Hello, everybody. My name is Jose Pablo Folch, and I'm going to be presenting transition constraint Bayesian optimization via Markov Decision Processes. Let's begin with some motivation for our work. In many physical systems, you want to find or optimize a quantity of interest. So, for example, here we have an environmental monitoring task where we're trying to find the source of maximal pollution, denoted by the star. However, we face constraints of the system that are not usually present in traditional optimization methods. So, for example, all our measurements need to be close to each other because we need to move the boat from one place to another. In addition, we want to avoid certain obstacles. So, for example, islands in this case. And we further imposed the constraint that we have an initial and a terminal state corresponding to docking stations in the lake. In this graphic, we can already see our algorithm in action and being able to solve this complex task. So let's begin with some notation and definitions. We have a search space or state space, calligraphic X with states X. We have trajectories in the environment, which are simply sequences of states. A state distribution, d pi of X, corresponds to the probability that we visit state X given we have deployed policy pi. The set of potential maximizers is going to be denoted as calligraphic set. The physical system or black box function is going to be F and is going to be modeled by a Gaussian process. And finally, the posterior mean of this Gaussian process at time h is going to be denoted mu h. So what is the goal of our paper? And that is to identify the optimal configuration of a physical system. And we do this via sequentially querying a black box function. And this results in noisy observations which are used to identify this optimum. However, the added difficulty in our work is that the sequence must respect the underlying transition dynamics. The contributions of our work are threefold. The first one is identifying a novel acquisition function or utility for maximum identification as a function of policies. We then minimize this acquisition function using convex optimization, and we're able to provide optimal Markovian policies at each time step while building overall non-Markovian policies via replanning. And finally, we provide empirical evidence of the strengths of our approach, both in real-world problems and in synthetic benchmarks. To derive the utility, we focus on choosing the trajectory of experiment style that will minimize the probability of not identifying the optimum. And in the paper, we show that this probability of an error, and actually the worst case probability of an error, can be minimized via the utility at the bottom, which corresponds to a hypothesis testing problem where we're trying to minimize the uncertainty of the difference in values in a set of potential maximizers. This set of potential maximizers we define by using the Gaussian process itself. So we begin with the whole space and we're slowly discarding points when we find out that the probability that the point is an optimum is very low. So we have this set of potential maximizers becoming smaller and smaller, allowing us to start exploiting towards the end of the optimization procedure. To actually optimize the utility, we cannot do it directly in the space of trajectories as this is untractable. We instead follow advances in convex reinforcement learning and exploration in Markov decision processes. And what we do is we are able to relax the utility we just described to the state of space to the space of state distributions. And this relaxation actually makes the optimization problem tractable, and we just use convex optimization to solve it. In particular, we use the Frank-Wolf algorithm. And by using the Frank-Wolf algorithm, we're able to obtain optimal Markovian policies at each time step. However, we actually want a non-Markovian policy overall. And to achieve this, we optimize a correction distribution to the states we have visited so far instead of optimizing distribution directly. And by optimizing this correction distribution at every time step, the overall policy results as non-Markovian because it depends on all past observations. Finally, we provide empirical results in flow reactor optimization, environmental monitoring, and electron laser calibration, which did not have algorithms that could perform well in any of these stacks before. We also do continuous Bayesian optimization benchmarks with local search constraints, and in these cases, we're able to achieve state-of-the-art performance. If anything you heard here interests you, please feel free to contact me at the emails here, or even better, come by our poster at NeurIPS or read our paper. Thank you very much for your attention.